right, welcome to the last video of Chapter 9, 9.10, Taylor and Mclaren Series. Our ultimate goal at the end is to write or figure out what the value of e to the pi I is. All right, so we'll come back to that, but we'll look at some Taylor and Mclaren Series for those. Okay, so we already talked about Taylor and Mclaren polynomials. All right, so these are very similar, but we're going to talk about the series that represent these. All right, so a Taylor series is going to be centered at C. All right, so the series is going to be the nth derivative of f at c over n factorial times x minus c to the n, and we can figure out all of the terms here. Now, a Mclaren series is simply a Taylor series when we're centered at c equals 0. Okay, so we're going to look at this, all right? Instead of the c value, we have 0. If we clean it up, we're looking at all of these terms here, okay? So what we're going to do first is we are going to write the Mclaren series for f of x equals sine of x, all right? So the first thing we're going to do is let's create that table just like we've been doing for the power series, and we're going to find all the derivatives and we're going to evaluate those when c equals 0. All right, so f of x is sine of x. Evaluating that at 0, we get 0. The first derivative is cosine. At 0, it's 1. Second derivative, we get 0 when we evaluate. Third derivative, we're at -1. And fourth derivative, we're back to our original function. So we can kind of see that it would just repeat itself. So remember, this is our constant. This is the coefficient of our linear term, of our quadratic, our cubic, and our quartic. So now if we were to go through and write that series, or begin to write the terms of this series, so we can write the series in and of itself, we have 0 plus 1 times x plus 0 x squared over 2 factorial minus 1 x cubed over 3 factorial plus 0 x to the 4th over 4 factorial, and so on and so forth. Cleaning this up, we can essentially just eliminate these guys because those coefficients are 0, so they're not there. Okay, so what we really have is x minus x cubed over 3 factorial. If you notice the pattern, the signs are just alternating, and we're dealing with the odd degree terms. All right, so plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial. And so now what we need to do is we need to talk about what the nth term is. So this is when n equals 0. This is when n equals 1, when n equals 2, when n equals 3. So can we go ahead and write for the nth term? Well, hopefully we recognize that this is an alternating series. So we're going to have -1 to the n, all right? And what is x being raised to? Well, hopefully you can say, oh, well, when n is 0, we have x to the 1st power. When n is 1, we have x to the 3rd power. So we should recognize, and etc., that we would have x to the 2n plus 1, okay? And then the denominator is the same as that degree, so it would be over 2n plus 1 factorial. So this allows us to write the series. So that would be our series for the sine function, okay? So we would say, all right, f of x is equal to sine of x, which is approximately this series right here. We were to add up all of those terms. All right, so let's take a look at the next page and identify some of the power series for some of the functions that we should memorize. Okay, so here's just a bunch of power series, okay, and what those look like. So it's going to help to memorize these three: e to the x, sine of x, and cosine of x. If you memorize those three, then we can use those to help us write power series for any combination of these guys. So for instance, let's look at this next example again, start memorizing these power series. All right, so notice e to the x, we've already talked about e to the x. Sine of x, we just came up with that one. All right, cosine of x, notice it's similar to sine of x. It's an alternating series, but now we're just focusing on the even degree terms. All right. Okay, so like I said, let's look at this next example here where we're going to create the power series for f of x equals x squared times sine of 2x. So we're going to use the knowledge of this sine of x and we're going to manipulate it so it becomes x squared times sine of 2x. So let's see what this looks like. All right, so the first thing I do is I start with our function or our power series for sine of x. So it's equal to the odd degree terms and we're alternating signs. But now I want sine of 2x. So instead of x, we now are going to input a 2x there. So it's 2x minus 2x cubed over 3 factorial plus 2x to the 5th over 5 factorial, etc., etc. Just kind of cleaning this up and distributing that power because it's going to help us in the long run. All right, we get 2x minus 2 cubed x cubed over 3 factorial plus 2 to the 5th x to the 5th over 5 factorial minus 2 to the 7th x to the 7th over 7 factorial, etc., etc., etc. Okay, but now our goal is to have x squared times this. So now we know what sine of 2x is. We need to multiply that by x squared. So I'm going to take every term here and multiply it by x squared. So x squared times 2x is 2x cubed. X squared times 2 cubed x cubed over 3 factorial is 2 cubed x to the 5th over 3 factorial. And so on and so forth. When I multiply x squared times this term here, we get 2 to the 5th x to the 7th over 5 factorial. And then x squared times this guy, we get minus 2 to the 7th x to the 9th over 7 factorial, so on and so forth. So this is when n is 0. This is when n is 1, when n is 2, when n is 3. So I want you to see if you can come up with the power series for x squared times sine of 2x. So the fact that it's alternating, we know we're going to have negative 1 to the n, all right? What about this 2? What's 2 going to be raised to? What's x going to be raised to? And what's our denominator factorial going to be? Go ahead, give it a try. When you're done, come back and check your answer. Okay, so let's see how you did. All right, so again, the series is going to start when n equals 0, goes to infinity. We've got the alternating series, so negative 1 to the n. 2 is going to be raised to the 2n plus 1. X is going to be raised to the 2n plus 3. And the denominator factorial matches the degree of our 2, base 2. So over 2n plus 1 factorial. Hopefully you were able to get that. All right. And now we're going to go on to the next one. Okay, so now we're going to create a power series for f of x equals sine squared of x. Well, we don't have this as a power series to memorize, but we know a trig identity. Sine squared is 1 minus cosine of 2x over 2, or we can rewrite it this way. So if we know what cosine of x is, which from the previous page or from memorization, we know it is equal to this, then all we have to do is manipulate cosine of x with this part right here, okay? So the first thing we could do is find cosine of 2x, all right? So cosine of 2x is right here. So instead of an x, everywhere there's an x, we're going to plug in a 2x, okay? So it's going to look like this right here. And then we have to multiply that by negative 1/2 because that takes care of this portion here, negative 1/2 cosine of 2x. So when we do that, we're going to get to this part right here, okay? And then we have to have this 1/2 in front. So it's 1/2 minus this whole quantity, right? Or now we're just kind of dealing with this whole fact right here. So what does that mean? Well, what we should notice is that the 1/2s cancel, all right? And when that's the case, now we're going to let this be when n equals 0. This term is when n equals 1. This term is when n equals 2. n equals 3, etc. So thinking about that, can you come up with the power series for sine squared of x? Okay, so remember it's an alternating series, so we're going to have that -1 to the n. Think about what 2 is going to be raised to, what x is going to be raised to, what your denominator is going to be. All right, so give yourself a little bit of time, pause the video, see if you can come up with that power series, and then check back. All right, hopefully you were able to get it. So we have the series from n equals 0 to infinity, -1 to the n, 2 to the 2n plus 1, okay, x to the 2n plus 2 over, well, the denominator matches the power of x. So it's going to be 2n plus 2 factorial. All right, so there we have it. So that's a way we can manipulate the series that we know to find any new power series. Okay, now like I said at the beginning, our goal is now to use or to find the value of e to the pi I using a Mclaren series. So the first thing I want you to do is I want you to write out the Mclaren series for e to the x. Okay, so first write out those terms, see if you can memorize it. And then, so I'll give you a second to do that. Go ahead, pause, and write out the e to the x power series. All right, so hopefully you remembered e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. All right, so now instead of just plugging in pi I for x, I'm going to change things up just a little bit. Let's go ahead and substitute I theta for x, okay? So I theta for x, and I'm also going to distribute that 2 to the I right away, that power, or sorry, the power to the I right away. So we're going to look like this, okay? Now, cleaning up these I squareds, I cubed, I to the 4th, all right, what do we get? Well, when we clean that up, right, I squared is -1, I cubed is I to the 4th is +1. So we're really looking at these guys. Now what we should notice is our signs are changing, okay? And if we kind of split this up, so if I just focus on this term plus this term plus this term, right, those three, we're looking at cosine. So we should notice that the even degrees, those signs are alternating, right? And so we get cosine. Now what we should also notice is that the odd degrees are also alternating, and that gives us I times the sine of theta, all right? So notice those odd degrees all have i's in front of them, and they would continue on. So what we really have is e to the I theta is really cosine of theta plus I times sine of theta. But now we need to plug back in. Instead of theta, we're evaluating this at pi, right? So cosine of pi is -1, and sine of pi is 0. So we really get -1 plus 0. So what does that mean? It means e to the I pi is actually -1. Who would have thought? Anyways, if you have any questions, let me know.